We are finally to derivative shortcuts. We have been finding the derivative by the definition, and now we are ready to get some properties that will save us tons of time. All right, so the first one says that if f of x is equal to a constant, the derivative of constant will always be 0. If you think about what the graph of y equals 5 looks like, that's a horizontal line. So if you drew a tangent line, you would get a horizontal line. What's the slope of a horizontal line? It's 0. So since slope of the tangent is derivative, that makes sense that the derivative at every point is going to be 0. So if they gave me 5 and said, what's the derivative? It's 0. If they gave me pi and said, what's the derivative? It's 0. Any number, the derivative is going to be 0. All right, the next one is probably the one we'll use most often. This is the power rule. And the power rule says that if you have x raised to a variable, you're going to move, you have x raised to an exponent. You're going to move that exponent out in front times x, and then you're going to reduce that exponent by 1. So, for instance, if you have x to the 6th, you're going to move that exponent of 6 out in front and then multiply times x, and then you're going to reduce that exponent by 1. So it would be 6x to the 5th. All right, look at the next one. So even if there's a coefficient out in front, it's going to work the exact same way. So I would still pull that exponent of 6 out in front, and I would have 6 times 2x, and again reduce that exponent by 1, so that that would be 12x to the 5th. So if I look at the next couple of examples, if I can find a way to rewrite them with an exponent, then I can use the power rule. So for instance, how could I rewrite the square root of x with an exponent? Well, I could write it as x to the 1/2, right? Then I can use my power rule because I can pull that exponent out in front, and so I'll have 1/2 x and then reduce that exponent by 1. So 1/2 minus 1 would give us negative 1/2. So we could write it 1/2 x to the negative 1/2, or if you'd rather take that x to the negative 1/2 to get rid of the negative exponent, move it down to the bottom, and x to the 1/2 is the square root of x. All right, then for the next one, how could I rewrite this with an exponent in the numerator? Well, to move across the division bar, I would just use a negative exponent. So 1 over x squared is x to the negative 2. So for the derivative of that, we can pull that negative 2 out in front and then reduce that exponent by 1. So negative 2 minus 1 would be negative 3. So you could write it as negative 2x to the negative 3 or negative 2 over x to the 3rd. All right, if you have f of x is equal to x, what is the exponent on that? Well, it's a 1, right? So the derivative of x to the 1, I'm going to take that 1 and move it out in front. That would be 1x. And my new exponent then would be 0. So 1x to the 0 is just going to give me 1. So we just discovered that the derivative of x is going to be 1. And of course, we'll use that quite often. All right, the next property says that if you have the derivative of a constant times a function, you can pull that constant out in front and just take the derivative of the function and then multiply by the constant, okay? So for instance, if we have 3x to the 4th, all right, if we were to use the power rule for this, where we take our 4 and move it out to the front, we would have 4 times 3, or 12x, and then we reduce that exponent by 1. So we know the answer we're supposed to get is 12x cubed. So then let's use that to see if this constant rule this coefficient rule works. So I could say if f of x is equal to 3x to the 4th, according to the coefficient rule, I should be able to take the derivative of x to the 4th get that answer and then multiply it by 3 and get the same answer we did a second ago. All right, so let's see. The derivative of x to the fourth would be 4x to the third. And then we multiply by the coefficient, and sure enough, we get that same answer, 12x cubed. All right, look at another one. The next rule is the addition and subtraction rule. It says if you have the derivative of two things that are being added, you can break that into two separate derivatives and then add them. Or if you have the derivative of two things that are being subtracted, you can break that into two separate derivatives and then subtract them. All right, so let's look at this next function. All right, so let's start with what's the derivative of x to the 8th? Well, that would be 8x to the 7th. And what's the derivative of 12x to the 5th? Well, 5 times 12 is going to give me 60, and then x to the 4th. So I had two things that were being added. I was able to take the derivative of this and the derivative of this separately and then just add them. All right, similarly for this next one, the derivative of 4x to the 4th, 4 times 4 would be 16, and then x to the 3rd. So again, when you have two things that are being subtracted, you can do those two separate derivatives and then subtract. All right, so then what's the derivative of 10x cubed? 30x squared. What's the derivative of negative 6x? Remember that that is 6x to the first, so 1 times 6 would be 6x to the 0, or just 6. Another way to think about that is to use this coefficient rule that says, hey, you can just take the derivative of your function and then multiply by the coefficient. And remember, we saw that the derivative of x was going to be 1. So another way to look at this is we could say the derivative of x is 1 and then multiply that by that coefficient of 6. All right, and then the derivative of 5 is going to be 0 because the derivative of any constant is 0. Now, we got to pause for just a second here and think about what this would have looked like if I had had to use the definition. If I had had to do f of a plus h minus f of a divided by h and then take the limit of that. I mean, a plus h to the 8th alone. Then let alone doing all the rest of this and trying to combine all those like terms and take a limit. And these shortcuts are going to be so time-saving and beneficial for us. All right, so now that we know how to use some of those properties, we can apply them to things that we've already learned. Like if they ask me, where does this equation have a horizontal tangent line? Okay, well, if you think about the slope of a tangent line is derivative, and what's the slope of a horizontal line? Well, the slope of a horizontal line is 0, right? So again, if slope of the tangent is derivative, then basically we want to know where the derivative is equal to 0. All right, so let's find our derivative. So what would the derivative of this equation be? It would be 4x to the 3rd minus 12x plus 0. So 4x to the 3rd minus 12x. All right, so now we're going to set that equal to 0, and we're going to solve it. All right, so take out your greatest common factor. You could take out a 4x, and then we can set each of those factors equal to 0. So if we set 4x equal to 0, divide both sides by 4. Set x squared minus 3 equal to 0. We'll add 3 to both sides. That would be x squared is equal to 3. And then to get x by itself, we would take the square root. Don't forget to put in plus or minus. So we would get x is equal to plus or minus the square root of 3 as well. And those would be the places that I would have a horizontal tangent line. All right, here are some more shortcuts that we can utilize. All right, so to begin with, they give us the product rule. If we have one function times another, or one monomial times another, and we want to find the derivative of that, we're going to do first times the derivative of the second plus second times the derivative of the first. And here it's written out in words as well, right? Now, just so that we can see that this works, if we were to go through and say, okay, I got these two monomials that I'm finding the product of, let's simplify first. Let's do 2 times 4 is 8. X to the third times x to the fifth is x to the 8th. What would the derivative of that be? Well, it would be 64x to the 7th, right? So since we know what the answer is supposed to be, now let's kind of do an informal proof to see that this property really does work by utilizing it and seeing if we get the same answer. Okay, so according to this property, it says take your first, 2x to the third, and multiply it by the derivative of the second. So the derivative of 4x to the fifth would be 20x to the fourth. Then add to that the second, so second was 4x to the fifth, times the derivative of the first. Well, the derivative of 2x cubed is going to give us 6x squared. All right, so let's simplify a little bit. 2 times 20 is 40. X to the third times x to the fourth is x to the seventh. 4 times 6 is 24. X to the fifth times x to the second is x to the seventh. So now we have like terms, and we can combine. So 40 and 24 would be 64x to the seventh. So you can see that that property really does work because I get the same answer here as I did here. One thing that I would stress to you is look how much simpler this is if you have any way of simplifying your function first before you start taking the derivative. So you always want to look and see, can you multiply things together? Can you go ahead and divide? Can you factor and cancel? Can you do anything that will make this simpler to work with before you start taking the derivative, even using these shortcuts? All right, here's another property. It is our quotient rule. And it says that if you have one quantity divided by another and you want to take the derivative of that, you're going to take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Another way that some people refer to this is they'll say low d high minus high d low. And what they mean by that is low is the denominator, high is the numerator. So they'll say low d high, derivative of high, low d high minus high d low, derivative of the low. So that's another way to remember it. Okay, so for this one, I look first and I want to see, is there any way to simplify this? No. But let's say that we did not have the 6 on here. Let's say it was just x cubed. I definitely could have simplified that into something much easier to work with, right? Because I could have said x to the second over x to the third is 1 over x. And I could have said x over x to the third is 1 over x squared. And then negative 2 over x cubed. If I write each of those with a negative exponent, I can use my power rule. There is no denominator, numerator, that kind of stuff. So again, that's the type of thing that we're looking for in simplifying. That doesn't work for this particular problem, but we have an example that we just discussed where it would. Okay, so for this one, let's take our denominator and let's multiply it by the derivative of our numerator. So the derivative would be 2x plus 1 plus 0, so 2x plus 1. So denominator times derivative of numerator minus numerator times the derivative of our denominator. So the derivative of x cubed plus 6 would be 3x squared. And we're going to put that all over the denominator squared. All right, so let's combine anything we can. These first two terms here we're going to FOIL. And so we'll have x cubed times 2x is 2x to the fourth. X cubed times 1. 6 times 2x is 12x, and 6 times 1 is 6. And then here, if we distribute, we're going to have 3x squared times x squared is 3x to the fourth. 3x squared times x is 3x cubed, and 3x squared times negative 2 is negative 6x squared. All right, so let's combine that numerator. So we can say 2x to the fourth minus 3x to the fourth is a negative x to the fourth. X cubed minus 3x cubed is a negative 2x cubed. I don't have an x squared term up here, but minus a negative 6x squared would be plus 6x squared, and then plus 12x and plus 6, all over that common denominator. All right, look at the next one. For the next one, it says, create the equation of the tangent line for the equation at the point 1, 1/2. All right, so if I'm going to find the equation of a tangent line, I have a point, what do I need? Well, I need a slope. All right, what is the same thing as slope of the tangent line? Well, it's derivative, so I can use these derivative shortcuts. So again, I want to look at this and see, is there any way to simplify this first? There's not. So let's use that quotient rule. So we're going to say denominator times derivative of numerator. Now, remember that we've already done the square root of x previously. We rewrote it as x to the 1/2 so that we could say 1/2 x to the negative 1/2, right? So denominator times derivative of numerator minus numerator derivative of denominator. So the derivative of 1 is 0 and the derivative of x squared is 2x, all over the denominator squared. Now, if I am evaluating this at a point, it is so much easier to plug in numbers and simplify than it is to try to simplify with variables, right? So absolutely, before you start trying to simplify this, go ahead and plug in your x value. So our x value was 1, so if we go ahead and plug that in, we're going to have 1 plus 1 is 2, and then 1/2 times 1 is 1/2, so 2 times 1/2 would give us 1. And then 1 times 2 would give us 2, and then down here 1 and 1 is 2 times 2 is 4. So we're going to end up with a negative 1/4. That is our slope, right? Okay, so now we have a point and a slope, and so we could use y minus y1 is equal to m times x minus x1 if you want it in point slope form. If you distribute that negative 1/4 and add the 1/2 over to the other side, then we would have slope intercept form. If they wanted standard form, we would clear out all of our fractions by multiplying by 4 and move it all over to one side. So whatever they ask us to put it in, we can do that.